Alright, hey guys. Today is round 714. There's a thing going on. And yeah, don't have much to say about this. Except for the fact that Codeforces runtimes don't seem to be trustworthy lately. They're differing by over like 700 milliseconds or something from what I've seen. So it's going to be a bit concerning, but I guess we'll see. Update the sub count as we always do. Let's get started. We have a permutation. I know. We have two integers ending k. Construct a permutation that has exactly k peaks. Okay. Why? What? It has to be larger than... So the maximum number of peaks we can have is like m minus 2 over 2, and then we can... Alright, that is not interesting. Cool. I guess it's just like do it. So the maximum number of peaks we can have is, like, suppose we have 5, then it's like m minus 1 over 2. If we have 6, it's also m minus 1 over 2, floored. If we have 4, we can have 1. Yeah, because if we have two peaks next to each other, then one of them is bigger than the other, so that's not really possible. So if k is greater than m minus 1 over 2, otherwise we'll say let's see, so it's ai equals point minus point minus k. If k equals 0, break. So first we like go by like odd indices and then just set them to the largest numbers, and then the rest will be the smaller numbers. And we can print. I was never able to type at the beginning of a contest. It just seems like something that happens. Oh, what? Why are there so many invalid cases? One, 2, 4, 1, 5, 3, -1, -1. So this is a peak, and nothing else is. And this is a peak, and this is a peak. Yeah, if we have 6 and we're asked to have 3, then it's not possible. Okay, that was kind of fun. Cool. Great. Okay, why? Exactly k peaks. Next time an array A of size n is said to be a peak if wait, what? Oh. That is a mistake. Okay. Oh, that's fun. Is there anything else I missed, or are we good? Alright, not a good start. Is it gonna get better? Sequence of n non-negative integers is called good if the bitwise and of the prefix is equal to the bitwise and of the suffix. Number of permutations p of numbers ranging from 1 to n, for which the sequence of that is good. So it has to be 0. Oh wait, we're given the sequence. Oh, what the hell? Okay, when is it not good? It's not good if the elements on the ends are what are important, I guess. Checking. Yep. Okay, I guess the numbers on the ends are what are important, so if there's some value that everything in the array is ANDed by, then like for example, suppose everything has 1, then we can sort of ignore that. So we can take the bitwise AND of the whole array, then like subtract that out from everything, and then we're left with some zeros or something. And so if we don't have a single 0, then we're screwed, and otherwise how does this work otherwise? If we do have zeros, then well, if we put the zeros on any end, we're automatically done. And otherwise, if we put any non-zero element on the end, then automatically we're screwed. Because when we take that element, then it's like, yeah. So how does that work? How does it come out to 36? Alright, because every sequence, every permutation is different. Alright, so really we're choosing 2 of the zeros, which is 3 choose 2. Then we're permuting them, actually. So it's 3p2. There's so much combo involved here. Why did they ask for so much? What kind of div 2b is this? It's just like math. It's annoying. Alright, so read in n. Still can't type. Don't know what's up with that. So basically you're removing the common and from everything because like because we don't need it, it's going to be present in everything. Then we count the number of zeros, and then it's like the number of zeros, choose 2 times 2. And then the remainder. The factorial of everything else. Ants equals C0 times C0 minus 1. If it's less than 2, automatically we're done. Otherwise, I equals 1, I is less than or equal to n minus 2, I plus plus. Ants is equal to ants times I mod mod. 36O. Oh wait, other way around. We need to modify the array elements. I don't think we overflow. So basically we put the zeros down. If we have less than enough zeros, then we're done. 130. 2. Yeah, so basically it's like entirely determined by the elements we have on the end. Okay, add 1, you have an integer m, an integer n, you have to apply some operations to it. To replace every digit with the decimal representation. Digit d plus 1. 1912 becomes 21023. Define the length of n. Okay, so all the digits are independent. M is small, which is important. Basically, all the digits are independent, so we can like do some stuff, and then we can, I guess, just like simulate it. Now we have too many test cases for that, but we can pre-compute like DP or something. We can say that DP of a digit and the number of operations left will become how many things that becomes. Sure. Okay, so this is something we pre-compute. DP of 10 and actually I can do something like 200,005, 11. Memset DP 0 size of DP. Alright, so DP 0I is equal to 1. Need the mod. So if we have this digit, it's every digit here is just going to become like itself plus 1. So dp of ij is equal to dp of I minus 1 j plus 1. That's what it becomes. And dp of I9 will become 1 plus 0. So dp I minus 1 for 1 and 0 and that. Because it has to be 1 and 0. That's how that works. dp m c minus o. Alright, cool problems so far. Loving this. Awesome. Yep. Alright. And again, yeah, this is just because it becomes a 10. And all digits are independent, so we're really just like tracing everything independently. Alright, that was easier than A and B. Nice. Or at least simpler. Cool. We're doing okay? We have that penalty, which is not nice, but yeah, worst. Alright, fine. I'll take that. GCD and MST, you want array A, with some positive integers and integer P, consider an undirected weighted graph of n vertices. What? To find the weight of the minimum spanning tree? Okay, so if the GCD is the minimum, if the minimum number divides everything, then there's an edge. Okay. I plus 1 equals j. Oh, that matters, I guess. I'm gonna save strong samples. That's something I can appreciate. Maybe it gets more interesting here. Yeah, I can clear this. I also don't know why I did memset, but whatever. So are we to efficiently simulate some algorithm? Basically, GCD equals min is essentially saying there's some number that divides everything. So I guess maybe we go through the numbers. How are we supposed to do this? I can build like a sparse table on GCD or something. But that's stupid. Is that what we're supposed to do? So we consider the numbers like in increasing order, like the array values, and we say like how would this work? If we have a 1, we're like instantly done, right? Yeah, so like how are we supposed to find this out? If we problem is not that like nice. So I can try and draw some stuff. Basically we're trying to find like we have this like graph. So like say we have like 2 for example. Then for everything to the right that we can reach, we can add the edge and like connect them. For everything to the left, we can add the edge and connect them. Problem is, of course, it's n squared, and like there's some other issues too. Like for all values greater than p, we can ignore. So that's fine. this isn't some messy DSU bash. That would be a pain. I suppose we have like a 3 here. Then we can have numbers like 6, 6, 3, and 3, for example. Like this 2 would match with everything. And these 3s would be able to match with each other. Oh, wait. To turn on the light for the laptop to charge. It's not even plugged in. Yeah, okay. I mean, I guess we can do something with DSU bash. Are people solving this quickly? If not, then I'll assume that's what it is. Okay, I'm gonna assume that's what it is. So in DSU, we can store a bunch of things. We can store the left and right endpoints of a component, and we can also store the GCD, and that way we start here. We go to this component, we try and connect them. If we don't succeed, then that means we have something that's not divisible by 3, or something that's smaller. Something that's smaller, or no, just something that's not divisible by 3 in general. So then we stop. Otherwise, we continue, we merge these components, and now we go to here, and we continue. So the thing is, like, is this something interesting? I mean, it'll work. It'll work in n log or n log squared or something. And the components will always be contiguous, because if we match this with an edge, if we don't match this with an edge, then like how would that even be possible? Like either these two are already matched by an edge beforehand, or they have to be matched by an edge now, because like the point of the condition is that it affects everything to the right that satisfies the condition. It's like a contiguous interval. Alright, well, I am greatly pained by this problem too. So maybe it's not the intended solution, in which case I can appreciate it more, but if that is, then that's just not nice. We multitests? We do have multitests, so we do need to do the vector stuff. Great. Gval equals vector ll. We do left and then right. Gval equals AI. We do that. Right. You can do iota, but like whatever. So actually I do need to be this. Can I speak? I do need this to be before. I can get rid of find because I've never used that in my life. And then we need to do some smart stuff with merging. So let's see. Gval marks B is equal to GCD of gval marks B, gval marks A. Then left marks B is min. Shine some light on how I can make this DSU more efficient, but whatever. It doesn't matter at this point. I just want to write this code and be done. So now it's the maximum. I don't think we need this anymore because we're never going to touch this component again. Yeah, okay. So C into N to P. I don't know what the point of P is. I mean, it's like very pointless. DSU D dot init n. Alright, now we can create like pairs of stuff. Why can't I type? Why did I type the wrong bracket so it auto indents backwards? PVI equals AII. So if at a certain point we have more than or equal to P, like we're basically efficiently simulating Kruskals, that's the idea. So we're gonna do some like edges and stuff. PVI.s C equals PVI.f, J equals PVI.s. Okay, now we're doing left and right. So LL is equal to lock while 1. Left value is equal to the d dot left of the mark of L. That's how my DSU works. If your DSU doesn't work this way, then you probably want to do something different. It's the left value of the marks to the left. Did I put an extra bracket there? I did. So if LV is less than 0, or the GCD value of d dot marks LV, actually this has to be -1. Mod C is not equal to 0. So it's not divisible by this number. Then we break. Otherwise, ants plus equals C, d dot merge LV L. So every point we're looking to the left of our current component, we look 1 to the left, we see if we can merge. Actually, do we need that specifically? No, we really only need the array value. Okay, so we'll save that. So really it's just like the array value of the rightmost thing. So it's A of LV. Yeah, so we can merge if that, otherwise we can't. Now we check this. So now we add the whole component in. So if this mod C is not equal to 0, then now we break. Do the same thing for this. So RV is d dot right. And this is +1. And this is RV is greater than or equal to n. We merge with RV, and then so we should check this. Am I not able to? It just forced me to do that? Alright, that's interesting. Okay, I'll do that later, Jesus. Alright, so actually, we need to, we only need to check this merge, I guess. Because when we do the merge, we check that it works before, we check that we can merge with at least one element, and then now we check that the whole thing works. What the hell? Why is it forcing me to do this? Alright, I will do it after the contest. Let me just record my video, my god. Okay, so if d dot marks L mod C is equal to 0. So actually first we have to check that we can even get out of our current component. And then if we can do that, then we try some stuff. Okay. Now for I equals 0, I is then minus 1, we're just gonna use the p edges, the edges with weight p. Ants plus equals p times d dot merge I plus 1. The times is just to like mess with some bit, like basically it returns 0 if it doesn't work, and if it is it gval, I did call it gval, so I should do that. D dot gval. When it makes sense to use just the marks. I don't know what that was for. Okay, I don't trust that, so let's. Okay, don't remind me again. Oh my god, I can fix it later. Okay, let's try this test that we had before. Actually, wait, that's interesting. It wouldn't ever cross. Huh, I just realized that. It wouldn't ever need to cross. Okay, maybe that actually makes it simpler. Maybe we don't need to do this DSU stuff. I think we might actually just be able to like iterate straight up. Whatever. Let's see, we're merging with that, we're merging with that, we're merging with that, min, max, etc. We iota these, set these to AI. Now, if we can start, now we know we can go here, so we're trying to go left. This doesn't work, does it? Because it checks both the left and to the right. Ugh. I don't think we actually need to do this though. I think we can, okay, I think I'm being dumb. I think we can iterate directly. If we ever encounter some other component, then it means it was merged by some smaller number. Or the same number, and therefore we don't have to worry about it. Okay, so all of this is pretty much useless. And really the only thing we need to do is directly iterate. So it's like for LL if d dot sizes d dot marks L is equal to 1. J equals L minus 1. So if d dot sizes d dot marks J is greater than 1, automatically we don't need to check anything. Break. Otherwise, if, because that means it was merged by something smaller than us. So if AJ mod C is equal to 0, and it's plus equals C, d dot merge J L. Plus 1, J is less than J plus plus. We can get rid of all this, I guess. $36. What? How does it do better? $36. What did we get beforehand? 12. What cost are we spending here? So if we have that, oh, else break. Right, because we need to stop otherwise. Because now we hit an element that we didn't get. Okay, for the purposes of simplifying, I'm just going to get rid of all this because it doesn't matter. Yeah, I'm pretty sure that just works. Or not. Okay, what's with that? So why? So if this thing is ever in a larger component, then it means we reached it with a divisor. We reached it with a divisor. Or the same number. In which case, that divisor will have an easier time like merging with others. If we merge into some other component, it also means we reach that component with a smaller number. And thus, either that smaller number is a divisor, and thus would have an easier time merging, or it's not divisible, in which case we can't get there anyway. Right? So we start here. We start at the smallest value, we iterate. And so that should be fine. Then we continue. We go to the what? Funny, these are the exact numbers I was thinking of using for that test. So if we're here already and we're in some larger component than ourselves. So what would have caused that? It would have been caused by being divisible by some smaller number. And otherwise there's no smaller number that can reach it. And therefore, maybe this is the problem. So there's no smaller number that can reach it. For example, suppose we're at some location. So there's no smaller number we can reach it, meaning that this may have to extend out and this may have to extend out. Because the fact that no smaller number can reach it means that, like, it's a horrible arrow, but the fact that no smaller number can reach it. Actually, if this isn't a larger component, it means it was reached specifically by a divisor, not a smaller number. Maybe we check this first. I think we check this first. That might be what we need to do. We check this first, and if that was in a size greater than one component already, yeah, that's kind of necessary. LV equals that. If V is greater than 1. Yeah, I think that was necessary. Also, useless sample. Yeah, very useless sample. It's plus equals C. Yeah, we try merging first. Cool. Alright, to the last problems. An array is called beautiful if all the elements in the array are equal. You can choose two indices and integer x. Let I be the source and j be the sink. Decrease the ith element by x and the jth element by... Increase the jth element by x. Resulting values at ith and jth index are that. I think this can no longer be the sink. Weird. So I will be the source. Oh, and the cost is the absolute value. And the cost is uniquely defined. So the minimum cost is equal to the maximum cost. What the hell does that mean? All permutations are balanced. Interesting. So it's like every element has exactly one choice. The samples again look useless, so that's not great. Resulting values, right. So we essentially pick some index. We're gonna move some stuff from here to here. Now we can no longer move any sort of stuff from there anymore. Or we can no longer move any stuff to there. We have to choose positive x. Yeah. What? So we can no longer move stuff to there, and we can no longer move stuff from there. So really, like, we consider the average. We consider the average value. Anything equal to the average. So basically, every element is either a source or a sink. It cannot be both by the constraints of this problem. So that means that everything less has to gain value, so it has to be a sink, right? Yeah, and then everything greater has to be a source. Now we're moving stuff from sources to sinks. And the way that will work is I guess we have ones and zeros now. Is that how that works? If we have multiple sources and multiple sinks, what makes it balanced? Oh. So either they're all on one side, or some other stuff is happening. So suppose we have something like let ones be like sinks and zeros be sources or something. And then essentially this can go here and this can go here. So it kind of depends on what has to feed into what, I guess. If some source is forced to feed into everything, then that means it's never... That means it doesn't matter what we do. Well, it kind of depends. Something forced to feed into everything. What does that mean about the other things? Not everything is forced to feed into everything. Like, for example, suppose we do this, and we do this, and we do this, and we do this. And that means that, like, we could instead, like, have this feed into that, and then have this feed into that. And then maybe one of these would need to feed into the other one, but not both of them. Like, whichever runs out first, essentially. But it wouldn't be both of them. Let's see, the things that are exactly equal don't matter in the slightest. So really we can put those anywhere. Is it true that the ones and the zeros either have to be like... Either we have exactly 1, 0, we have exactly 1, 1, we have all 2's, in which case that's automatically done. Or... Like, if we have more than 1, 0, how would it ever be possible? Because we can take some, like if we have, for example, 1, 0, 1, 0, right? So we can, like, find some valid sequence that does the balancing, and then just swap some of the things. Like, for example, we can move 1 unit. We can say, instead of moving 1 here, this guy, so like this path will lose 1 unit, and then this gains +1. And then what that means is that this path will lose 1 unit, and then this path would gain +1, and then we'd have a higher cost. Is it always true that that's the case? I kind of like feel like it would be. Intuition says it would be. Don't have a. It seems hard to prove though. Seems very annoying to prove. But I mean, it exists. Seems very, very annoying to prove. I guess like you can always take some. Yeah, some like two valid operations and swap them. Or two valid like ordering, two valid whatever it is, the balancing sequence of operations, and then mess with it a bit so that it changes the cost but doesn't change the effectiveness. So that can happen if you have 1001, then that can happen. Specifically, you can like, if you have 1001, then you can decrease this one going to here, and then decrease this one going to here, and then increase that and increase that. Because either they both go here, they both go the opposite ones, or they both go to the adjacent ones. If they don't, then like how would that even work? So yeah. And then for this, you can like move one of them to the right over or something. Like if something's not crossing this one, you can make it so it does cross this one by moving whatever this is over. I'm pretty sure it's just like a ton of casework, which is awesome. So cn to n s plus cn to ai s plus equals ai. So if s mod n is not equal to 0, automatically we have no answer. S mod n is not equal to 0. Alright, otherwise it is. Set the average, so if this is less than the average, AI equals 0. If AI, else, if AI is greater than average. Else because we're modifying them. What do we do with the 2's? How does that work? I mean, it's like we're assigning locations to them and then we permute them. So I guess like, say we have C0, C1, C2. We don't have multi-tests. I can get my mod app in so we can do some sort of factorial stuff. Right, now if count 2 is equal to n, it's simply fact n otherwise. If we have exactly 1, 0, or 1, 1, 1, count 1 is equal to 1. Note that because of the way this works, we need to have at least one of each of 1s and 0s. So that's cool. So if either of these work, then any valid ordering is possible. So actually, in this case, it's still n factorial, because any valid ordering is possible. Otherwise, only the valid orderings which have all 0s on one end and all 1s on one end, or all 0s on one end and all 1s on the other end at work. So ants equals 2. So we have C0 plus C1 plus 1 locations. And they really just hate us with the samples, don't they? And we have C2 things. So therefore it's by stars and bars, it's C0 plus C1 plus C2. Choose C2 times C2 factorial because we can permute them, right? So we have that many locations. We can put them in any bucket like separated by them because we don't care where the C2s are. Then I think this always works actually, but whatever. Well, it's always the number of ways to arrange the C2s. Two times, so it's NCK N C2 times fact C2 mod. So it'll work for samples because it'll work for samples, but does it work for everything is the question. Let's see. So so we have 1, 3, 2, 2. So the answer here should be everything. Yeah. If I get rid of this, it should still work. Doesn't work. What? Because it should be count CT, not whatever the C variable is. 24, yeah. So 1, 2, 2, 3, because yeah, we can permute them in any way. We can stick the 2's in any way we want, then we can permute the 2's any way we want. It's like 5, 4. Choose 2. Yeah, that makes sense. That totally makes sense. We're choosing locations for the 2's, then we permute them, of course. Let's see. 4, 1, 2, 2, 2. Good. Don't know if it works. Hopefully we're doing the mod right. 10 to the 9th plus 7. There's a lot of combo here. Using that as mod. Using my pre-written factorial template. Oh no. Cool. What's with that? So again, the 2's don't matter. So we're solving only for the 1's and the 0's, and we need to figure out how many orderings we have. Then we can factor in the 2's at the end. Alright, so what's with that then? Top R 6 1 3 3 2. Essentially the way that works is we have 2 times 6 choose 2. Yeah. So that would fit my formula, but it doesn't seem like it works. Have any dumb mistakes? So we generate the factorial. Printing S. Yes, so we add the sum. If the sum mod n is not 0, is it integers? Yeah, integers. Oh, wait, it's not. Wait, what? It's not the number of permutations. It's, wait. This is just like totally. What is it asking? Is it the number of arrays or the number of permutations? I guess it's the latter. That just makes it even more annoying. Okay, so we actually get rid of this part. So if we have all 2's, then all the elements are the same. So this is actually 1. So if we do that, then ants is equal to n. This is annoying now. Why did they had to make it annoying? I don't understand what the point of that is. Count. If AI, let's have this be like B or something. If BI is greater than, less than 2, then plus plus C BI AI. So we do that, ants times fact count 0 mod. I'm gonna do the same thing for this. It's like, really, these samples are absolutely awful. It's like, how does this work? Oh, yeah, okay. So for, can I trust iterating through maps? I'm not sure if I can trust that with how volatile Codeforces has been, because I got screwed by that earlier too. C0 ants is equal to ants times inv of fact. Actually, it should be just like ifact x.s. And the same thing here. I think it'll work. What? We get 3. If count 2. Wait, what? That shouldn't matter. We get n times... No, it shouldn't be n, it should be n minus count 2. Yes, because the 2's don't matter. We're solving for everything but that. So we get this. Alright, this is sort of an unclear statement, sort of a misread, I don't know. So let's redo these cases. So now we still have that, except now we don't permute them. So we can basically, like, we have 4 choose 2 ways, which is 6. Then we put the rest of them down. It should be 12. Yeah, 6, so 1, 1, 2, 2, 3, 3. So we really only have 2 ways to do that. 6 choose 2 ways to do that, so it should be 30. So like 8, and like, I suppose our average would be 5. Then we have like 1, 3, 3, 5, 5, 7, 7, 9. So then what that will do is we have to put that on the end there, or that on the end there. So we have 2 times, let's see, 3 times 3, 18, times 8 choose 2, 28, 18 times 28, so we have 504, yeah. I should try just reading this statement again. Decrease the ith element, increase the jth element. The cost of a transformation is the sum of all the costs. Yeah, I mean, we get past pretest 5. I guess we do. Okay. So that's a thing. Given 2 arrays A and B, both of size n. Where are we right now, actually? Guessing some people have AK'd, some have not. Geothermal doesn't have F. Interesting. Okay, not so bad. Pretty bad. Not so bad. Pretty bad. Relative to everyone who has A to E, pretty bad, but like not many people have A to E, so it's not so bad. What did I mess up on D? Oh, right, it was that. Okay. Alright, let's look at this last problem. You have 2 arrays A and B, both of size n. You can swap 2 elements in B at most once. You're required to minimize the value sum of AI minus BI. Absolute value of AI minus BI. Seems like a buttload of casework. That's a pain. This is 3,500 points. Just like, where are we right now? Yeah, I seem to always be slow on these things. Close that off. close that out. Right, so swap two elements and be at most once. So guessing here you swap these two. So we fix some element. Got messed up. Fix some element, then there are like a lot of cases or something, right? So we fix the value in B. This is an annoying way to finish off. We fix some element somewhere A, we fix some element in B. So now essentially what happens is we're looking for the other element in B. So there are like a lot of cases. Specifically, we can break down the absolute value so that we say, we suppose first that we're going to where this is greater than this. So blue is greater and purple is greater. Like this is greater than this, and this is greater than this. And the cost is the cost we save rather is nothing actually. Yeah, it's nothing. Interesting. So both are greater or both are less, we actually do nothing. Because yeah, it's just like adding and then subtracting. The cost doesn't change. Interesting. So really we need to pair a value such that this is greater and this is less, or vice versa. And then we would swap those and then, yeah, it would change. Maybe we could still consider all cases. Or are they like, it's only nothing if they were all like all graders in the beginning. Okay, I mean we can sort A. Does that help at all? Can do this breakdown of stuff. So let's ignore the initial costs. Somehow we can handle that later. So if we ignore the initial costs, then blue will be greater and purple will be greater. So it's like overall elements where this is greater than this and this is greater than this. I want to minimize it. Minimizing is the problem. If it was maximizing, we'd have an easier time because we actually could ignore the cases entirely. Because if we're on the wrong side and we're solving for maximum, then it would be negative, and therefore it doesn't matter if we get it wrong. But with minimum, it does matter. Because negatives would make it smaller, and that's better for us. So we can't do that. So we have to do all the cases out. Ugh, yay. So if blue will end up being greater and purple will end up being greater. How do we like even do this? When the cost is simple, it's like say like this is greater and this is greater. And this is like negative and this is negative. Can we do this grouping somehow? It's like, it can be done with like a 2D segment tree, but that's not gonna be nice on the time. Sorting by A doesn't really help. Not really. I guess we can, let's see. Assume we iterate in increasing order of A. So maybe we do sort by A. Assume we iterate in increasing order of A. Then, or we iterate over we iterate over some element in increasing order of A. Then the other element, we can sort of like, for some period of time, they will be less than our current element, and for the rest of time, they will be greater than. So we can solve for less than and greater than separately. Had to be 10 to the 9th, didn't it? It really just had to be. Like, they just had to make it as annoying as possible. Because why not, right? Because why not? Why not? Why not? Why not? Seems like a good philosophy. Could write an implicit segment tree if I really have to. It's a pain, but I mean, it works. So really we're moving some elements over. So now this element, we independently solve for when the other element is greater than whatever this one is, and when this is less. So then the cost then will be like either positive here or and negative here, or negative here and positive here. We can figure that out. And the variable part is this. So for all things where this is greater, then this has to be negative and this has to be positive. And then for all where it's less, yeah. Is this gonna kill me if I do an implicit segment tree? 512 megabytes. I mean, should be fine. I just don't want to do like, some random code. Let's close off this stuff. I don't want to do coordinate compression and like mess with that stuff. It's just like a pain. Because it requires binary search too. So maybe this is easier. But it's also just a pain. Like, why did they... Like, them making it 10 to the 9th is just like a personal touch or something. update. Read in that. Sort p equals n. We don't care about the initial order. So L_ants is equal to 0. Initially we save nothing. We're interested in the cost we're saving. So we do some magic at the end of it. Ants plus equals abs pi.f minus pi.s. Yeah. Okay. So this is 200,005. We do b for the same thing. PBI is equal to p. Actually, wait. Do these in the modified indices. pi.si. Okay, so now is it worth it? It probably isn't. I don't even know if we can squeeze implicit signature here. I'm pretty sure we can't, actually. I think this is just not going to work. It's just way too slow. Could try and optimize it, but I don't have the time right now. Let's just do normal signature. Signature from int. Actually, that's not so bad, I guess. It's not the worst. So keep segment trees min t st. We need 4 of them. So 4 I equals 0, I is less than 4, I plus plus st I over 2 I mod 2 dot init memset c0 size c and c. Okay, now each thing initially ends up in the first. So 4 I equals 0, I is less than n, I plus plus. For each thing in PB, actually wait, this should be like massive. Sure. Okay, so this is like that's a note to myself that I will maybe understand. Or is it us, them, actually? No, it's them, us. So assume these are all less than our current value. Right, so the second thing is, are we larger? So st st, so it's 0 0 dot update, make it smaller. So the cost here will be, we're assuming that blue is somewhere. We have some purple element and we're figuring out the cost for blue. The blue cost is this, the purple cost is this. So if blue is going to be larger, then this is negative this, and this is, if this is going to be smaller initially, then this is negative this. So the value we get is negative pi.f minus pi.s minus cent. Now here we assume that this value, actually wait, no, wait. These are the values that are less, right? Wait, how does this work? Oh, it matters in A. Oh my god. Ugh. This is very annoying. Yeah. Cool. So right, so essentially this we assume is smaller initially. So actually this arrow should be directed this way, I don't know. Doesn't really matter, I guess. Gonna leave that for now. Just like an arrowhead, something. Yeah, that's not what it was. That's not what the word is, whatever. So this is larger. So initially for this, we query over everything to the left that's smaller than it, and then we query everything that's larger than it. So yeah, it should be negative. And then here, this is 1. And so now this is larger. We still assume this is smaller for the time being, and later on we will move it over to the larger one. So this is, the first should be positive. And this will be at I, that. Actually, wait, no, it should be the index in terms of B, right? No, it's the index in terms of A, so that's fine. All right, now we iterate over the value. Well, point is equal to 0. So while point is less than n, and now we're interested in when these values become smaller than this. No, larger. Wait, so this should all be 1. What am I doing, man? What am I doing? So we start off with them all being larger, then some of them will gradually become smaller. Right? Yeah. So then 0 is like it's going to be less, and 1 is it's going to be larger. There's no way I'm going to make this pass in 30 minutes. But we'll try. So while point is less than n, and the value, the b value, pb point.s, is less than or equal to the current value, which is the current b value. No, wait. Current a value, pi.f. We move it over. Well, j is equal to pb point dot s. So this is j, 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 j. J, 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 and J. Right? don't trust myself here. I really don't trust myself. So this assumes that the b value will be greater than the initial a value, which is true, and for all of them, and therefore the second should be added positively because this is greater, and if this is less, then it'll be that, and if this is greater, then it'll be that. Then we do a segment tree query to the left of everything less and to the right of everything greater. So it makes sense. It does make sense. Then we negativize this because now we're removing it. Negative. And we send them both to 0. So now this becomes that, this becomes that. And this is no longer negative, this is no longer negative, and now this is less and this is less, so we get that. Yeah. Now we do the querying, so LLL equals 0, R equals N. So we need to do some binary search. Binary searching on the value of A. So while L is less than R, M is equal to L plus R. Cannot type for the life of me. So we're looking for the first index that's like less than or equal to. First index that's strictly larger. Actually, it doesn't matter, but first index that's strictly larger. So if, what is it? So it's simply like pm.f is less than or equal to pi.s, L equals m plus 1, else R equals m. So now we query everything. Yeah, so if L is greater than 0, ants equals min ants st of 1, 0 dot query from the value 0 to L minus 1 dot val. And that assumes that the array value is greater. No, it's that the b value is greater and the a value is smaller. So because the b value is smaller or greater, this is negative pi.s plus pi.f. Right? We're querying for such an element such that this is larger, this is smaller. So this should be negative, this should be positive. It's minus pi.f. Yeah. So the b value is larger, and therefore this a value should be smaller. Okay, we do the same thing, but now we query the ones where the b value is smaller, and therefore this becomes positive. Yes, the b value is smaller than this a value. If r is less than n, ants is equal to min ants st, so 1 dot query r to m minus 1 dot val plus, no wait. So both should be negative, minus pi dot f minus pi dot s. We do the same thing except for 0 and 1. The only thing that makes sense now is that this should be positive and that should be negative. Alright, because the previous b value is smaller and therefore this is larger. No way it works. Absolutely no way it works, but 12. Okay. Is that the initial cost? So really we're finding nothing? Yeah. So what am I getting here? Let's test the binary search first of all. Cout I, L, and O. You can also print the pairs. Because why not? Can't hurt. Test it here because that doesn't work. It's not really doing anything is the problem. So 0 and 2. Yes, that is correct. And 1 and 1. Yes, that is also correct. So we're getting the right query. Cout I. What do we get here? Just worry about left right now because everything will have a left, so we might as well check that. So it's always Sentinel, and that's not helpful. Why is it adding that? What if I just don't do this? What am I querying right now? Oh, wait, I see. Okay. So that's fine. Something's being messed up here. Oh wait, it said I also have to subtract out the initial costs. So LO cur is equal to 2018. Make this cur instead. Right, so here the cost also has to take into account abs pj.f minus pj.s. Right. It should be I, and I. Still get 4. Because I don't do anything. Ants equals min, ants cur minus pi. Never get 2. Should get 4 here. Yeah, okay. No way I can trust that though. So let's just look at this a bit more. So 1, 5, negative 4, 2, 4, negative 2. Is that true? We initially had this cost. We can move that here. No, we do save 4. That's fine. Problem is this is better. Yeah, I see. So this doesn't help anything. Fine, 1, 2, 3, 4, 5. Should be able to save 2. How does that work? Yeah, we should be able to save 4. Alright, so first of all, 1, 1, 5. Should be 5, yes. 2, 4 should be 4. Yeah, so it's pretty much everything. So 3, 5, 3, 5, 1, 1, 2, 2. Yes, yes, yes. Okay, good. pi.si. Is less than 4 plus plus. So I divide by 2, I mod 2 dot init and c. For I equals 0, I is less than ni plus plus, I 0 dot update. So 1, 0. Again, so we're assuming that this value of b is going to be larger. So if we add this value of b, and we subtract out that value of a. Now, for the ones where now this value of b becomes smaller, and because we sorted by that, this should always happen in order. So then what happens there is that we remove that cost, then we add it to 0. Now this is where the b value is smaller. So we assume that this current value is like going to be larger. Yeah, so the b value is smaller. So we subtract out that b value. And we move things over. Yeah. And this is 1, 0, so this b value is larger, meaning we have to subtract out our current a value. This b value is smaller when we add in our current b value. Should all be positive. And then this b value is smaller, meaning we add in our current a value. I don't know, probably will get wrong answer, but just kind of want to try it. Could FST also, that's a thing that could happen. I assume it'll get wrong answer, actually, that's the default. What? Wrong answer on pretest? Oh, because I have all these debug prints. Yeah, okay. That was anticlimactic. Let's see. I'm going to pretest 2. I'm going to pretest 9. Is it going to work? Guess it worked. Alright, that's a thing. Cool. Where does that put us? 26th. Alright. Pretty solid rank throughout. Not by any means the most fun problems, but we still got them all, so. Wow, some huge deltas by some of my friends. That's crazy. And then some less huge deltas, but that is how it goes. The balance of life. Now, let's see. Did I enjoy anything here? Was there anything nice? I don't even know. So A was like, do it, pretty much. I don't know if the peak thing is interesting. Maybe it is. This is at least there's some sort of logic involved where you fix the end elements. This one's straight DP. This one, I don't know. It's like something. There's more data structure work than like actual observation stuff though. This one was just a guess, to be honest. And this one was segment tree. Woohoo! segment tree. I love those. Absolutely love those. Love doing tons of indexing and stuff like that. Surprised it worked on the first try though. So let's see, Gabe pretty much beat me in everything. That's fun. What took me so long with B? Oh, it's just like a thing that happened. Alright, anyway. I think we could have been faster, but like at this point it's not that important. We got everything. It's good. What the hell? Did you just like win the round or something? Yeah, you got third. That's pretty whack. Anyway, am I close on any of the runtimes? Am I gonna be screwed over again? 11 to 7 milliseconds, and it's 2. Who knows? Who knows? Who knows? Who knows? There are 30 pretests. That's a lot. I think it's pretty decent. Do feel bad for people like Second Thread though. Who actually wait? He's using Kotlin now. Oh, it is Java. Still. Is anyone else using Java? Not that I know of. It's the last person here. RIP. Okay. Well, I have nothing more to say. Let's do solutions. Alright, in this we have a number n and a number k. We want to create a permutation such that it has exactly k peaks. A permutation of length n. And a peak is simply a number that's not on the ends, meaning that there is a number to its left and to its right, and it's greater than the number directly to its left, and it's greater than the number directly to its right. So for example, we can draw out 2, 4, 1, 5, 3. So this is 2, this is 4, this is 1, this is 5, this is 3. Then we connect these with lines. And then just visually, this is a peak, this is a peak. This is not a peak because it's surrounded by 2 larger elements. This is not a peak, and this is not a peak. If I added some smaller element here, this would be larger than this, but not larger than this, so these 2 values are the only peaks. So basically in this construction, really all we need to do is we say that like, if some element is a peak, then that means it's strictly larger than the elements to the left and right of it. Meaning that the elements to the left and right of it by default cannot be peaks. So suppose we stick a peak on, it sort of like screws over the elements to the left and to the right of it. So really we can only have like, we can't have multiple peaks in a row, meaning the best we can do is we can put like a peak at like the first index, and then the next peak we can put is not at 2, but at 3, and the next peak we put down is 5, and then 7, and so on. So really that's like it. We put these peaks down, and then like if we've put at least k, or like if we ever get to k, then we're done. If we never get to k, then we don't have enough spaces for the peaks, and we also have to make sure you don't go on to the end. So you can't be at 0 and you can't be at n minus 1. I'm using 0 indexing because that's what normal people do. And yeah, that's basically all this problem is. You go through the odd indices, you put peaks down greedily. If you have enough, you're done. If you don't, then you can't. And be careful about 0. That was the edge case that got me this wrong answer. So it's not really an edge case, it's just like don't write dumb code. So an explicit formula for the number of peaks you can have is it's the floor of m minus 1 over 2, I believe. For example, for 5 we can have 2 peaks, for 6 we can have 2, for 4 we can have 1, etc. So really, if k is between 0 and this, then it's possible, and if not, it's not. So how do we, like, implementation-wise, how do we put down peaks? Well, for the numbers that we designate to be peaks, we can basically just put down, like, the largest numbers. So we can start with n, and we can put down n at position 1. And we can put down m minus 1 at position 3, and then m minus 2 at position 5, and then m minus 3, etc. And then in the other positions, we can put the smaller numbers, like for example 1, and then 2, and then 3, and then 4. And so we guarantee that every green number, every number we designate to be a peak, is going to be larger than the other numbers, because we're putting them down in that order. So code-wise, it's basically that simple, sort of. We check the upper bound. If it's not possible, we print -1. I set everything to -1 for implementation's sake. Then basically we start at n, we put down a value, make it the largest possible, and then do that, and everything else will be a smaller value. So everything that isn't designated to be a peak can thus be everything else. Note that it will not be a peak on the end. Say we have 7 and then 6, and then the green values are 5, 4, and then 3, 2, 1. Note that this is strictly decreasing, so this is the only value that could potentially be a peak, but it's next to this larger value. And if we have no peaks, we'll simply construct the array 7, 6, 5, 4, 3, 2, 1, which of course has no peaks. So this sort of construction will work. We go through the odd elements, we put stuff down, and then that's it. Okay, for this one, it's sort of like a weird condition. Basically, we have an array, we want to figure out the number of permutations of this array. So the number of reorderings, basically, where even if we have 2 reorderings that produce the same array, if the reorderings are different, then it's different. So basically if we the 0 at position 1 and the 0 at position 3 are functionally different, even though their AND values will become the same. So we need to count those separately. So we basically need we need to reorder the array. So we have some positions. So that at every point between 2 elements, the prefix, the bitwise AND of all elements on this prefix is equal to the bitwise AND of all elements on the suffix. And this has to happen for all points that are in between 2 elements. So for example, this has to be equal to this, the bitwise AND over these. Bitwise AND over this has to be equal to the bitwise AND over this, and that. Okay, now the idea is what? So suppose the bitwise AND of the whole array is x. Let x be the bitwise AND of the whole array. Then no matter what we do, every prefix and every suffix will have x as a submask. Meaning basically we can sort of ignore it. We can sort of ignore x because that's going to be everywhere. So implementation wise, you can either use x directly. What I did was I just subtracted out x, so that basically we're working with only the bits that we care about. So in implementation, you can subtract out, you can find this bitwise AND of the whole array and then subtract it from everything. So now the only other thing that really matters is, suppose the thing to focus on is the endpoints. Specifically, when are we having 1 versus everything else, and when are we having the last one versus everything else? If this number is 2, for example, we know because we already got rid of the bitwise AND of the whole array, there's some element on here that doesn't have the bits in 2 set. Therefore, the bitwise AND is not going to contain 2 on this suffix, and therefore it's not possible to have 2 be on one of the ends. This works for any number greater than 0, because the bitwise AND is now mandated to be equal to 0. For any number, any positive number we can have, there's going to be some number on the other side that's not going to have that, because the bitwise AND is 0. So really, what we're saying here is that the ends of the array have to be 0. They can't be any other number. So if we have less than 2 of zeros, then the answer is 0. Otherwise, any configuration where the two ends are 0 will automatically work, because for any suffix, it's going to have this 0 on it, meaning the bitwise AND is going to be 0. And for any prefix, it's also going to have this 0 on it, meaning the bitwise AND is going to be 0. So that basically does it. As long as we have 2 zeros in the end, it's necessary for the array to be valid, and it's also sufficient, meaning that that's it. So we just need to count the number of arrays that we need to count the number of permutations that have 2 zeros in the end. So say we have say we count the number of zeros. Okay. Now basically the number of zeros we can choose is, well, we can pick any of the zeros for the first one. So really we have count 0 ways to pick the first 0. Then we can pick everything. We can pick anything except for the 0 we first picked. Note that order does matter, so it's not C0 choose 2. Then it's C0 times C0 minus 1, and that's the number of ways we pick the zeros. Then for everything else, we have 2 elements on the end, and thus we have m minus 2 elements everywhere else. And thus what we get is m minus 2 factorial. So the code then is just implementing this. We count the zeros, the answer is this, then we take m minus 2 factorial. It's a lot of more combo than I would have expected from a div2b, but I guess that's what they're doing. Alright, this one, I don't know what this one was. Basically you have a number, like say 1912. You're going to do m operations to it. Every operation, you take each digit and move it to the next value of that digit. So the 1 would become 2, each 1 would become 2, each 2 would become 3, and the 9 would become 10, which is significant. Then you do another operation. Now each of these digits in the 10 are independent digits. So now we have 3, for example, we have 2, we have 1, we have 3, and we have 4. Right, so we're interested in the length of the final number, not the value itself, but the length. Because the length can be huge, so it's not going to work if we print the actual value. Maybe it would work modulo, but it's not worth it. So because we're interested in the length, suppose we know what's going to happen to 1 after we do m operations. Note that because this operation relies only on a single digit, that whatever happens to this 1 is completely independent of what happens to this 9. And what happens to this 9 is completely independent to whatever happens to this 1. And what happens to this 2 is completely independent of everything else as well. Because the operation solely focuses on the value of the digit itself and nothing of the surroundings. So really we're solving independently for each digit. We're basically asking, after m turns, what happens to digit x? So now suppose we try and figure this out. So we, for example, have a 3 and then we have 20 turns left. So this 3 will become a 4 and then we'll have 19 turns left. And this 4 will become a 5 and we'll have 18 turns left. And eventually it'll become a 9 with 14 turns left. And then it'll become a 1 and a 0, both with 13 turns left. So really if we define this function to be this problem we're solving for, if I can find my mouse, the f of m and x is that. F of m and x is, after m turns, what happens to digit x? Or rather, after m turns, how long of a number will this value produce? So for any number that's not 9, then basically in a single operation, we go up a digit and we go down a turn. So that's it. F of mx is equal to f of m minus 1, because we have 1 fewer turn, and x plus 1. And if x is equal to 9, then we still have 1 fewer turn, but now we have a 1 and a 0. So we have to sum up both of those individually. Because when this 9 becomes a 1 and a 0, now again, this 1 and this 0 are two totally independent things. They'll produce independent lengths. So f of m and x is equal to f of m minus 1, 0, plus f of m minus 1, 1. Oh wait, this should be an equal sign. Right. So now that's basically it. This is a DP occurrence, so we can just like do that. You can either do memoization, which is very simple, or I pre-computed it at the beginning, because doing it for each test case is going to take like a very long time, because the sum of m can be massive, so don't do that. You can simply pre-compute it, and then the answer is for each digit independently, we add up the DP value for that digit. So the answer is like the sum over I of f of m and like the digit at I. So basically this DP is just implementing this occurrence. Initially, also f of 0 and anything is equal to 1, because if we do no operations, it'll just be one digit, it'll be itself. And otherwise, DP. Perfect. So anything less than 9 is that, and 9 is specifically that. Again, memoization also works, so I'm sure that's possible. People could have done that. Alright, now we have D. And D basically asks, let's just break down this condition right now. The GCD being equal to the min means that the minimum number is a divisor of all the other numbers. Like by definition. By definition of GCD, the minimum number is a divisor of all the other numbers. Meaning everything must be a multiple of the minimum value. And we need to create the MST of this graph where an edge between two nodes exists if the GCD of the values on the subarray is equal to the minimum, and then the cost is equal to the minimum. Right, so we need to find the minimum spanning tree, which is interesting. So the basic idea is we're going to simulate, and also between every adjacent pair of nodes, we have an edge of cost p. So basically, we need to find the minimum spanning tree of this graph. So consider Kruskal's. What do we do in Kruskal's? Kruskal's is basically greedy, right? We look at edges in, just drop my pen. We look at edges in order of, chair is so loud. We look at edges from smallest cost to largest cost. If we look at each edge, if the two nodes of this edge are not already connected, then we connect them. And then we take that edge and we connect them. So not connected, I'm basically just like briefly outlining Kruskal's. So if they're not connected, take that edge. Meaning we gain the cost of that edge and then we connect this two. Then connect the two. And then if they are connected, do nothing. Or rather, don't take the edge. I guess I can say that. So like connect the nodes. So visually, we have two nodes. We're considering some edge of weight c. So if in the spanning tree that we've already built, if somehow these nodes are connected already, then there's no point in taking this edge because we've already connected these two. So this edge would only serve to connect these two, meaning that like there's no reason to do that. And if they aren't connected, then Kruskal's algorithm claims that the optimal way to connect these nodes is through taking this edge. This is true. I'm not going to prove it because there's many proofs of Kruskal's online, but that's the idea. So basically, we need to like smartly simulate Kruskal's. So how's this going to work? Well, we know that the cost of an edge is going to be equal to the minimum element. Meaning that for Kruskal's to work, what we need to do is we need to iterate over the minimum element from smallest to largest. So now consider some minimal element. We're going to connect it to everything that it isn't already connected to. Note that if we have two elements, like for example here and here, such that they have an edge between each other because this works, because this GCD is equal to this min, then so is this, then so is this, and so is this. Or rather, like, this should include this. This subarray works, and this subarray works. Because these GCDs are equal to this, and this is the minimum already, so it works. So therefore, the only edges we need to consider are really, like, the edges between this, between everything and the minimum. We don't need to consider this edge. And that's basically just, it's because of the way like Kruskal's works. Like if we were to, like the basic proof of that is if this was connected to this and this was not connected to this, then we can connect these for the same cost as connecting this. And if these are connected to each other, then we already don't need this edge. And if nothing is connected to each other, then instead of connecting these two directly, this is also not connected to this or this, so we might as well do that because otherwise we'll have to connect this either way. So really, like any possible way we can do the connections, we can make them happen using only edges from the minimum to everything else. So this is the minimum. So really we just need to say, for each minimum, connect it to everything that it works with, to the left and to the right. The problem is that's n squared. At least. Could be worse. Could have a log on it, but clearly that's not going to work because n is big. So we need to do better than that. How do we do better than that? Well, the idea is, suppose this has an edge to it from somewhere. So suppose this is in some component that's larger than 0. Oh, by the way, an implementation note, the way we implement like quickly checking not connected and connected, we use this thing called DSU. I'm not going to explain that because that's like too much for one explanation. So if you don't know DSU, you could probably search it. Probably a lot of good tutorials online, stuff like that. Anyway, we're using DSU, or disjoint set union, or UFDS, or like there are a lot of things people call it. So yeah. So basically, we use the DSU to check if this is already in some component that consists of not itself. What does that mean? It means that we already know there's some edge from some smaller element, or some smaller or equal element, such that like let this value be y, let the value that it has an edge to be x. Then we know that because we already had this x from edge to y, that x is a divisor of y. So x divides y. So either x equals y or x is less than y. If x is equal to y, then actually in both of these cases, any node that y would have an edge to would also have an edge by x to it, if there's an x between edge and y. Because the condition is that everything must be divisible by x. And if there's this edge here, we already know that everything in this interval is divisible by x. So if something has an edge to y, then it also has an edge to x because it's the exact same condition over here. And similarly, it's the exact same condition over here. So if this node is already in some component that's greater than itself, it's connected to some other node, then this is sort of obsolete. We don't need to consider this because we've already considered everything this node could connect to via some other variable. And if x is less than y, then we have even more freedom. Even more things will be divisible by a smaller value. So it's even better. By the same argument, suppose we're like strolling along and connecting y to some stuff. Like suppose we go here, that's cool. If this works, we connect it. And if it ever doesn't work, we can stop. And then we continue along here. Now suppose we have some other node that's connected by some value. Once again, we know that it's some other value. Suppose it's x. This time x doesn't necessarily have to be a divisor of y. Because like for example, y could be 3, and then we could have connected these via 2 or something. And this could be 6, for example. So both of these would work. The first thing we can do is maybe we can match it to the end element. Maybe we can match 3 to 6. But then the idea is whatever this x is, either x is a divisor of y. And then by the argument we made before, we can stop here because anything we can access from y, we can also access from x. So there's no reason to keep looking at y. We're done. We've already done everything we could with y. Or x is not a divisor of y. By the way, this just means x divides y, I think. If my notation's wrong, I'm sorry. But x, it means x, I'm trying to say x is a divisor of y. If x is not a divisor of y, that means x is less than y. Which means that, which also implies that y is not a divisor of x. So what that means is we can't go past this component. Because when we do, we're going to eventually hit this value x, and x is not going to be, x is not going to be divisible by y, meaning that we can no longer do the connection because there are no more edges past this point. So the argument is if we ever hit some other component that's already size greater than 1, first we try connecting to that component if it's possible, if there's an edge. And then once we process that component, we stop because we know there's either no point going past that component or we can't anyway, based on this sort of casework. So the algorithm is actually surprisingly simple, assuming you do have DSU implemented. So we go through the values in increasing order of AI. If AI is greater than P, then we stop because every edge will be of length greater than P, but that's not necessary because by Kruskal's, we can process the edges of weight P instead and do better. Then, so if AI is greater than P, stop. Otherwise, process in increasing AI. If it's already in a component of size greater than 1, stop. Otherwise, go until, let this be y, go until either we hit some x such that x is not divisible by y, or we hit some other component of size larger than 1. And then we could try connecting to that component if this value of x is divisible by y. And then immediately we stop because for one reason or another, there's no point to continue looking past this component. Either it's not possible or we already looked at it with some other divisor of y. And we do the same thing to the right. The reason this works complexity-wise is because every iteration, except for the point where we stop, is productive. Like every iteration will merge two components. Meaning that in total, the number of iterations we do is only linear because there are only n-1 total merges we can do because we start off with n component and each merge decreases the components. And then maybe we do like 2 extra because we have to stop. So it's like linear. A linear amount of times we go through edges. So really the complexity is dominated by sorting or DSU, however that works. Yeah, so implementation wise, this is DSU. You can either copy mine or like understand it for yourself, however you want. We read in the values, we create a list of pairs of the array values and their index. We sort those. Then we go through the array. We go through the values in increasing order of A. If it's greater than or equal to P, we can stop because we might as well take those edges. Then if this component size is 1, we go to the left. We store the component size of the previous one because it might change if we merge it. Or this is the component size of the one we're looking at. Now we try and merge. If it's not divisible by C, it's not possible, so we stop. And if this component size was initially greater than 1, then we stop. Then we do the same thing going to the right. And the final part is we consider all the edges of size P independently, and we use those if they're necessary. And then I have my merge return a Boolean value so that if we merge, then if we can merge, then it means that they're in separate components, so we used this edge, and otherwise we didn't. It's also possible to like count the number of components and just like that's the answer, but it doesn't matter. Oh boy. Let's see, have system tests started? Yeah, D is running, nice. Alright, so we got A, B, and C. Something like we didn't have that great of a penalty by then. Not that great. But we will pass this, I hope. Yeah, we got it, okay. People tried this? Yeah, wrong answer. See, it definitely seems easy to mess up. F. I don't know why I didn't mess it up. I didn't deserve to not mess it up, but somehow I didn't. So that's awesome. Cool. I think this is too large, so I'm gonna have to zoom out. Nope. Perfect. Okay. So we have E. E is weird. Basically, we have like a bunch of values. Let's say we have some like amount of objects in each value. What we want to do is we want to move some objects from certain positions to other certain positions so that all the objects are the same at every value. What we can do is essentially we can pick some place that we're going to send objects from and pick some place to send the objects to. Then we send those objects. Then now, after we do that, we place a constraint on the things that we used, basically saying this cannot receive objects anymore, and this cannot send objects anymore. So when something receives an object, it can't send any, and if something sends an object, it can't receive any. So basically, what we're saying is, initially, we preliminarily designate every node as either a sender or receiver or something we do nothing with. So we have senders, we have receivers, and then we have things that we do nothing with. And then we're going to figure out some arrangement of sending values from the senders to the receivers. So what we need to do is, we need to figure out the number of reorderings of the array. And what that means is like, unlike in B, which apparently I didn't understand, unlike in B, the array values matter. So like, suppose we have an array with 2 3s. Like, if we take the initial mapping, where the index 1 maps to index 1, index 2 maps to index 2, and we map index 1 to index 2 and map index 2 to index 1, these are the same. These are considered the same, so we count them only once. So we're interested in the number of distinct like arrays, not the number of distinct ways we can permute the array to make it work. So that's sort of an important distinction. And I think the samples are absolutely useless in that regard, so thanks, I guess. Yeah. They're absolutely useless in clarifying that, at least. Does that look better? I don't even know. Right, so what we need to do now is we need to count the number. This is like a really weird contrived-ish problem. We need to count the number of ways we can reorder the elements, or count the number of distinct arrays that can be generated by reordering the elements, such that Oh yeah, and the final part about this like process that we do to make all the elements equal is that we the cost is the number of elements we move times the distance we move them. So if we move 3 elements from here, then the cost is 3 times the distance 2. And then the total cost of a set of operations is the sum. The total is the total, of course. So we're interested in the number of ways we can do this reordering such that every cost is, or like, for all ways we could possibly do this, for all ways we can possibly send some elements from send some objects from some positions to other positions so that they become the same. For every sequence of operations that valid, they need to all have the same cost. So that's the statement. Yeah, so now we figure out what it takes. So we need to find the number of reorderings where this works. Okay, now the idea is, let's compute the average value of the array. Let it be x. And the average is of course the sum over the number of elements. If the average is not an integer, then we can only move integer number of elements. So if the average is not an integer, or if the sum is not divisible by the length, then there's no answer at all. No possible reordering would work. Otherwise, let this be x. Now the idea is every element greater than x has to be a sender because it can't receive values. It has to decrease its load by sending. Every element less than x has to be a receiver because that's the only way it can increase. And every element equal to x does nothing, pretty much. So in terms of the weird condition where we have to make the cost unique, so there's only one possible cost, the values that do nothing don't really matter. And because we're reordering, basically we're only interested in the number of ways we can reorder the senders and the receivers. And then we can factor these things that do nothing in back later. We can ignore them for now and then worry about them later. So now, what's valid? Let's go through some cases that aren't valid. So for example, say we have SR, S, R. So now suppose we're sending some amount to here and sending some amount to here. Now the idea is we can take any valid sequence of operations that makes the array valid, and we can swap some of them. For example, we can say we do one less here. We move one less from here to here, and we move one more from here to here. Which means now, from this, we have to move one more from here to here, and one less from here to here. And note that it gets the same effect, but it adds 2 to the cost. So if we have this as a subsequence, and if we have this as a subsequence of the things we're doing, then it's going to be invalid, because we can have multiple costs. Similarly, if we have something like this, then maybe we can have something like this and something like this. Maybe we have even more. But the idea is we can do the same strategy. We decrease this by 1 and then say we increase this by 1. Then we decrease this by 1 and say we increase that by 1. And thus now we have, again, 2 extra cost. That's sort of the best proof I have. This seems very hard to prove formally. I'm sort of interested in what the editorial has to say. If they gloss over the proof, I'm going to be mad. But so basically intuition says that as long as we have sort of these as a subsequence, then it's not going to be possible. Note that both of these subsequences require at least 2 R's and at least 2 S's. And note that if we have exactly one receiver, then no matter what, every sender is only going to send its stuff to that receiver, and there's nothing else we can do with that. Like, there's nothing we can change about that. That sequence is fixed. There's only one possible sequence of operations. Therefore, there's only one possible way to have a cost. And similarly, if we have only one sender, then that sender has to send it to everything, and there's no other way to have it done. So if we have one receiver or one sender, then all work. All of them work. Otherwise, what happens? So basically, imagine like we're putting stuff down. We start with an S, for example. Then suppose we put down a receiver. Now if we put down another receiver, then if we ever put down another sender over here, it means we're going to get this subsequence and it's going to not be valid. Meaning that once we put down two receivers in a row, we have to put down receivers for the rest of our life. Otherwise, suppose we don't have two receivers in a row. Suppose we instead put down, after we put down this receiver, we put down this sender. Now, because we're only working with the case where we have more than two receivers and more than two senders, eventually we're going to have to put another receiver in this interval. And what that means is we're going to have this as a subsequence. We're going to have SRSR. Meaning that it's not possible at all for us to put a receiver as the second element unless everything else we have is receivers. So if we put down a sender, then we put down a receiver, everything else is like forced to be the receiver. So that has to be the case. Or we can put down another sender and then we go on without a care in the world. That we can put down senders as much as we want. And then when we put down a receiver, everything else we have to do has to be a receiver. If we ever put down another sender, we're going to have some sort of bad subsequence. So all the senders have to be before all the receivers. Or all the receivers have to be before all the senders, for example. And the reason this always works is because, like, we can think of it like no matter how we reorder their operations, everything's going to sort of like move through the middle. So like we can say, for example, this sender is going to send all its stuff through this barrier. And this sender is going to send all its stuff through this barrier, and this barrier, and this barrier, and this barrier. And it's not the middle, it's like the point between the senders and the receivers. Now, however we do this ordering, all it really affects is what goes from this barrier to what. So for example, if we reorder it a bit, this can go to here, and this could maybe go to here, and this can maybe go to both of these, and etc. But the point is, the sum of the costs is equal to the sum it takes to get from these senders to this barrier, and then the sum it gets from this barrier to these receivers. Meaning that however we order it, it's going to be the same. As long as this barrier exists, as long as we have all the senders on one side and the receivers on the other side. So really, and note that this works because like we know that we have like the total number of objects that go through this barrier is the total that we're sending, and the total that get received is the total that we're like receiving, and it's sort of like independent of each other on one side and the other side of the barrier. We move all the objects to the barrier, and then somehow we distribute them from the barrier to everywhere else. But we have to have the same number of the number of objects each receiver gets is fixed, meaning that the barrier cost is fixed, and similarly the number of objects that we send is fixed for each sender. That's the basic idea. I guess that idea is kind of maybe interesting, but the point is like, so either we have exactly one receiver and exactly one sender. So then every possible reordering works because there's only like one way to do it. Otherwise, if we have at least two, the only way to do is to have all senders on one side and all receivers on the other side. And if we have no senders, then like, it also means we have no receivers because it means that every element has to be equal to the average. So having no senders is equivalent to having no receivers, meaning that if one's true, both of them must be true. So if we have no senders, clearly all of them work because we can do anything. So now basically this gets reduced to like basic combinatorics. We have a certain number of senders and a certain number of receivers. Either these senders are at the beginning or they're at the end. So we have 2 times, and now essentially we have a bunch of distinct values. We're looking for the number of permutations that's like, we're looking for the number of like distinct orderings of these values. So basically the value is the number of permutations. So it's, let's say like we let count s be the number of s we have. It's the count of s, except like say we have like 2 4s and 3 5s. Like this is probably something you already learned, but just to rehash it. Like for example, say we have 2 2 3 3 3. Now every permutation is going to count this, it's going to overcount because it's going to count this twice. Specifically, like it's going to potentially have the first 2 and the second 2, and then it will have the second 2 and the first 2 in that order. So these are different by permutation, but like visually they're the same. They're both 2s. And similarly for here, we have 3 factorial ways to order this, so we overcount by 3 factorial. So we have to divide by the product of the factorials of the counts of each element with respect to like the ones that are the same. And then we do the same thing for the ones that are receivers. It's like the count of AI with respect to receivers. Like we're only considering receivers here because senders and receivers are independent at this point. And then finally, now we also factor in the elements that do nothing. And so really it's like we're choosing locations for the elements that do nothing, and everything else is whatever. Everything else will work itself out. So we choose locations for the things that do nothing, because the things that do nothing don't affect anything. Any sequence that's valid will still be valid if we have some unused elements in there. So then it's the number of ways to choose the places for the things that do nothing, and then times the number of sequences that are like everything else. So it's really n choose the count of nothing, or it's the count of s plus the count of r, depending on how you do it. So in implementation, I had 0 represent the number I had 0 represent sender. No, wait. 0 was receivers, 1 was senders, and then 2 was the count that does nothing. So I think I'm pretty sure you can actually just like get rid of all these cases, but I had them anyway. So if everything does nothing, then the answer is 1 automatically. Also, if the average is not an integer, then we have no answer. So initially the answer is 2. Then if either the number of senders or the number of receivers is 1, then the answer is simply we have all the senders and all the receivers, and we can put this receiver anywhere. So the number of places we can put this receiver is CS plus CR, which is either count 0 plus count 1 or n minus count 2, either way. So then basically it's just doing this math. So it's either 2 or CS plus CR, depending on casework. Then multiply that by the count of like n choose count 2. Then multiply that by the factorial of the number of senders, the number of receivers, and then divide by this stuff. And then that's the answer. Be careful to do modulo operations right. So yeah. Did anyone know FSD? How did my rank go that much down? Wait, what? What happened there? Oh, was it always that? I don't seem to remember it always being that. But, oh yeah, I guess I checked it like a while ago, so maybe it must have gone down a bit. Oh wow, second, third failed system test. Time limit exceeded. I guess Java. We must have done something worse, like some sort of messy DSU thing. Anyway, all right, we have this last problem. It's kind of a pain. So it's very much a pain. It's very, very, very much a pain. So let's just get it over with. Statement's really simple. You have two arrays, A and B. You can swap two elements in B. You want to minimize the quantity of the sum of absolute differences between respective elements of A and B. Okay, so the absolute value is annoying. If we didn't have an absolute value, we can do some sort of like... The basic strategy for these like minimizing stuff is if we're gonna like fix some I and then pick some J that corresponds to I, what we want to do is we have some cost that corresponds to I and some cost that corresponds to J. And maybe this is like constant. So for example, suppose it wasn't absolute value. Then we would initially have AI minus AJ, or like AI minus BI plus AJ minus BJ. Then when we swap them, it becomes, for example, AJ minus BI plus AI minus BJ. So the change in cost is the difference between these. AJ minus BI plus AI minus BJ minus AI minus BI. This is all pointless. I'm going through this just for like the sake of what we're trying to do here. This is sort of the inspiration for what this strategy is. Right? So then we can mess with this equation a bit. The point is we want to isolate the I parts and the J parts so that everything with I is together. Because note that everything with I, because we're holding I constant, is a constant. So we're really trying to pick the minimum over all J of this cost. Which is equivalent to saying, because Ci is constant, we can take it out. We can say Ci plus the minimum over all J of Cj. And maybe this is easier. Maybe counting these Cj's is like a lot easier to do. So let's continue. If we write this all out, we get AJ minus BI plus AI minus BJ. Because again, this is the new cost, this is the old cost. Or this is the new cost, this is the old cost. So it's like this minus this is the difference in cost. So minus AI plus BI minus AJ plus BJ. It's very messy. Some stuff cancels out. For example, we get this. This cancels out. This cancels out. Actually, everything cancels out. So yeah, actually it turns out that it doesn't change at all. But the point is like, okay, that was a stupid example. But the point is we would isolate... This entire thing is pointless. We would isolate the I parts, right? So we'd have like AI minus AI plus BI minus BI. Ignore the fact that they're all zero because that's stupid. And then like, I guess it'd be plus like AJ minus BJ, or minus AJ plus BJ minus BJ, right? So we have all the I parts isolated, meaning that this is constant. So we're really just trying to minimize or maximize or minimize this quantity over all J, or I guess minimize. So this is Ci, this is Cj. Note that Cj also doesn't depend on I, meaning that at every J, immediately we know what it is. Right. So we can't do that though, because we have absolute values. So there's no real way to separate stuff in the absolute value. So the idea is, let's look at the definition of absolute value, right? So like absolute value of A minus B. It's like a piecewise function, basically. I think that's the notation. So it's A minus B if A is greater than or equal to B, and otherwise it's B minus A if B is greater than A. Or rather, if A is less than B, let's put it like that. It's also the maximum of these two. We don't really need to consider that. But, ooh. So what if we note that this is something we can separate, and this is something we can separate. The problem is we have to constrain it to this. But what if we did? What if we were somehow able to efficiently do that? What if we could say, so we have some I, we have some J. So we're swapping these. And we have AI, BI, AJ, and BJ. So the idea is suppose we force that we're matching a BI to an AJ that's less than it. And suppose we force, for example, that we're matching BJ to an AI that's greater than it. Then we immediately know these costs. The cost we get is the difference in costs we have is the new cost we have is BI minus AJ plus BJ minus AI. And then it's the difference between the old cost we have, which is minus AI minus BI minus the absolute value of AJ minus BJ. What the hell was that? Right, so in this spirit, let's separate this. Let's separate I's and J's. So specifically, we get BI minus AI minus the absolute value of AI minus BI. So this is entirely dependent on I. So we're looking for the minimum over all J plus BJ minus AI, minus AJ minus AJ minus BJ. This is some cost dependent on I. This is some cost dependent on J. Meaning that if we can have some sort of segment tree or just a running maximum or some set or something, whatever, however we can take the minimum efficiently, then we're really just looking for over all J's that satisfy this, that satisfy BI is greater than AJ and BJ is greater than AI. We're looking for CI plus the minimum over all J of CJ. So we just need to aggregate this efficiently over all J's. One way to do that is with a 2D segment tree. Let's not do that because that's such a pain and it's very likely gonna not pass the time limit. Because I already used over a second with a basic segment tree. Or lazy, I guess, but doesn't necessarily need the lazy. But the point is, this is something we can do. So if we fix the first element that we're going to swap, and then we try and optimize the other element we're going to swap with, we can find that. So now somehow we need to do this smartly. We need to efficiently maintain everything. So the way we can do this is we can say, let's say we solve for AI increasing. Increasing. What? Then as we sort of sweep across A, what's going to happen is that initially all of the B values that we're matching to I, so specifically initially all BJ are equal to AI. The equal doesn't really matter, you just need to make sure you stick it on one side so you don't ignore it. So initially we assume that all BJ are greater than or equal to AI. Then as we increase AI, some of the J's are going to move into BJ being less than AI. But note that every J only moves exactly once, and they also move in the order of J. So we can really keep an array sorted by B. We can keep an array like this and then sort that. And then we can keep a pointer on it, and then as we increase A, we can also figure out which elements of B we need to change. So really now we're solving for two independent buckets. We're solving for BJ being greater than or equal to AI, and we're solving for BJ being less than AI. So now we need to figure out AJ and BI, for example. So what do we do with, so now we basically have now 4 cases, as always. We have these 2 cases, and then within each of these 2 cases we have the 2 independent cases where we relate bi and aj. So for example, suppose that bi is greater than or equal to aj. Suppose bi is less than aj. Suppose that bi is greater than or equal to aj here, and suppose that bi is less than aj here. That's the idea. Now, it's not the nicest to implement. So what we do is the way we do this is we're like moving a, what am I saying? I don't know. Basically, bi is fixed. And we're interested in querying over all aj that are less than or equal to it, what's the minimum value of some quantity. And again, the quantity is whatever cost we derive for that j, for this sequence of inequalities. Like whatever is smaller is going to be subtracted. So in this case, the new cost we get is bj minus ai plus bi minus aj in this case. And like in this case, you'd swap these, and then in this case, you would swap these, and etc. Right. So basically, we're querying over all aj smaller than it, so we can use a segment tree to map values of aj to the cost, and then we're basically doing like an RMQ, like a range minimum query. The minimum over aj being less than or equal to bi over that. And then for this, we're basically solving for the minimum of aj being greater than bi. And essentially, you can use binary search to figure out the range of the segment tree that this corresponds to, or some sort of coordinate compression, or something like that. A lot of things will work. So with that in mind, with that, it's a bunch of segment tree operations and a lot of being careful about pluses and minuses. So I don't have much more to say except for implementation. Working this out is an experience you might want to have for yourself. So I keep a segment tree. So it's sort of like a bit convoluted. This represents, the first index is a 0 if the value of b is less for the j, and then it's 1 if the value of b is greater for the j. And then this comment makes no sense, I think, so ignore that. But this is saying the value of a is greater if it's 1, or the value of a is less if it's 0. So initially we start off with everything being a value of b that's greater. Then as we move on through a, we move some of them over to, we remove them from the 1. And then we move some of them over to 0. What if this works? Are they all distinct? If they aren't distinct, this doesn't work, actually. Oh wait, no, it doesn't matter. No, it doesn't matter because the index I'm using is simply the index in the sorted array by A. So there's no overlap. Okay, good. I was sort of confused about that. Then we use binary search to find, for the value bi, we find the position in the A array that it would correspond to, so that we can do like these queries. We can find over all aj that are less than or equal to bi, and over all aj that are greater than bi. Specifically, this searches for the leftmost element that's strictly greater than that. Then we query to the left, assuming that aj is less than or equal to bi, and do math according to that, and we query for the right, assuming that aj is greater than bi. And at the end, this stores the amount we save by doing a swap, so we have to add the initial costs, and then that's our answer. I don't know if there's ever going to be a time where I'm like good enough at this for it to not be messy. I don't know. Maybe there will be, but not right now. So I guess that's just how it is. Like, I always doubt myself when I do these problems, and like I never trust that I have the pluses and minuses correct, because the entirety of this hinges on whether you get the pluses or minuses correct. So the important thing is that we force that this be relative to j, then like a 0 corresponds to subtracting something and a 1 corresponds to adding something. And then like here, this is, we also have to add the values for a here, because again, or like for I, because again, we're separating the values for I from the values for j, but we still have to add the values for I in eventually. So it's very hard to track when we do this separation. It's very hard to like it's very hard to check that you're doing the right thing. Yeah, basically with a, everything that's a 0 corresponds to a plus, everything that's a 1 corresponds to a minus, and it's just super messy. Not that fun to work out, but we did. Somehow we got it, so cool. I guess that's it. I don't know if I'm gonna do the edgy round coming up. I'm gonna try and do 715. That'll be cool. Am I still? Yeah. Okay. I'm not gonna worry about that div 3. That one is just a mess right now. So I will leave it at that. Goodbye.